Welcome everyone. Hello. Okay. Welcome everyone. Can you guys hear me? Welcome everyone. Today's speaker is Professor Robert Kopp. You can see him up there on that tiny screen. As you can see, he will present you remotely. A positive trend in our field, motivated by two, I think, important things. One, the need to spend more time with our families and have a better work-life balance, especially if you travel, if you're invited to present a lot. And also be mindful about the resources that go into air travel. So first I want to thank Mark to organize all this setup. It's the first time we do it, so I welcome your patience if any glitches arise. But I think it's something we should keep doing going forward. Bob got his PhD in and a Master's of Science in Geobiology at Caltech. And he has been a professor at Rutgers since 2011. He has uncommon or unusual postdoctoral experience. He was a AAAS Science and Technology Policy Fellow at the Department of Energy for a few years before going to Rutgers. And he was also an environmental policy, a science, technology, and environmental policy postdoctoral fellow at the Wilson School at Princeton. He's now the director at the Institute of Earth, Ocean, and Atmospheric Sciences at Rutgers. And he's the co-director of the newly created Coastal Climate Risk and Resilience Initiative, also at Rutgers. And he's one of the PIs leading the Climate Impacts Lab, an initiative to translate climate information into actual economic impacts of climate change. Bob will talk about his research on sea level rise now. And if you're interested in talking with Bob directly, we're going to have a question and answer sessions at 12:30 local time at the second floor conference room at UTIG. Lunch will be provided, so there's 5 slots for lunch. If not, bring your own lunch. And Bob, it's all yours.
Great. Thank you all.
Bob. Yeah. Excuse me, Bob. Bob will explain how to interact with him in the Q&A. You can ask questions because there's microphones in the room. So you have to be clear and speak slowly so you can go through the internet. But he also is going to provide an alternative way to ask questions.
Yes. Yeah.
He can see you. Yeah, there's a camera there. So look at the camera. Yeah. So everyone can see each other. Bob, all yours.
Thank you. Hi, everyone. Thanks for being here today, and thanks for participating in what's actually an experiment for both of us. This is the first time I have taken a talk that I've usually given in person to places, and tried to transform it into an electronic talk, which, as was already said, I think is important both for work-life balance issues. I have a 15-month-old who doesn't appreciate me being away from home for extended periods of time, and also has part of the effort to sort of walk the walk and reduce our carbon emissions that are associated with the process of producing climate science. So I want to start by nodding to my friend and collaborator, Catherine Hayhoe, who's really sort of been pioneering this way of doing talks for several years. And I turned to her for an advice when I decided, I wanted to start doing more of this too. One of the things that she relies on a lot that we're going to experiment with today is online polling systems, because I can see your faces, but you're a little small, and so I can't get quite the same feedback visually as I would get if I were there in person. So what I'd like you all to do for a moment is so let's switch with me to poll everywhere. And so I want to get a sense of who's in the room today. So if you all would take out your computers or cell phones and respond either by text or poll to the poll on the left, we will hopefully find that it works and I get a sense of who's in the room. And then if it works, we're going to use this system to set up as our back channel for you to ask me questions as we go along. Ordinarily, if I were there in person, I would ask you just to interrupt me to ask a question. Maybe a little hard in this format, but if we get this working, I think it gives us a way of doing the same thing so that I don't get too far ahead of where you all are. So hopefully, as people start to respond to this, we will start to see some answers popping up on the screen.
Seeing the poll.
Oh, you're not? No. Okay. What are you seeing on your screen?
It says, welcome to our presentation. As soon as you click display the poll.
Okay, hold on. Let me try doing this a different way then. Thank you for, as I said, thank you for bearing with me. I think this will be useful. If it doesn't work, we're going to call it quits on this in a minute, but let me see if I can activate it through the web. All right. Is that working for you now?
Yes.
Yes. Excellent. All right. Great. So then two more sets of questions. So I see we mostly have faculty in the room, but also some postdoc and students and one or two community members. Let's go on and ask me a couple more questions. So one, I'd like to know what it is you're studying. Do we have a room full of people who have a lot of experience in sea level, in which case I will shape my talk a little bit differently, or working in a different field. So hopefully, good. We're seeing some results here. One, glaciology. All right, and now one more question to help me figure out where you are in terms of climate science background. Could you confidently describe RCP 2.6 and 8.5? All right, so I will make sure I don't assume, I assume people know what I'm talking about, and we will do that. It looks like we're sort of a significant number of you do, but not everybody does. All right, good. So then I'm going to set up one more polling question, which is basically just going to be our back channel. So if we use nobody needs to respond to this now, but if you have a question that you might ordinarily want to interrupt me to ask, I'm going to ask you just to text it here. So I can sort of get a view of it. So at the same address. All right. So now we're going to go back to the presentation. All right. Good. All right. So Let's start with something I think everybody here does know, right? We are living in an extraordinary time. For over 800,000 years, carbon dioxide concentrations in our atmosphere have stayed between about 180 parts per million and 300 parts per million, sort of giving us this glacial, or responding to this glacial interglacial cycle. In 1913, carbon dioxide concentrations surpassed 300 parts per million, and in spring 2014, they surpassed 400 parts per million for the first time in well over 800,000 years. And barring extraordinary efforts, they will continue to be above 400 parts per million for centuries to come. Let's look at that a little more closely, because even though I spent a lot of time thinking about this, there are still things that shock me when I sit down and look at this curve. So we're going to look at the CO2 since 1750 from the Law Dome ice core record and from the Mauna Loa direct air samples. Right. So in 1750, carbon dioxide concentrations in the atmosphere were about 750 parts per million. By 1850, they had risen to about 287 parts per million. So an increase of 10 parts per million in about 100 years. We had a similar increase of about 10 parts per million between 1850 and 1900. And going forward, again, the next 50 years, we had again an increase of about 15 parts per million. So a similar amount. And then we see a real shift starting after World War II. Sorry. Apologies. Between 1950 and 1984, we saw an increase in carbon dioxide concentrations of about 30 parts per million. Now, why are the 1980s of particular interest? Well, it's in the 1980s that this really became a policy concern. You know, we had the first congressional hearings on climate change with Jim Hansen and others, and then in 1988. And I just want to think about the number from 277 parts per million in 1750 to 1984. We had this increase of about 70 parts per million. In the last 34 years, we've seen the same increase that we saw from 1750 to 1984. So even though by the 1980s this had become a topic of policy concern, we've seen in the last 35 years, basically what we had previously seen over the previous close to 230. This still shocks me when I think about it, because we think about climate change often as a problem that's accumulated over time, but most of the increase in greenhouse gas concentrations at about the pre-industrial level has happened since the mid-1980s, in my lifetime, and I'm not that old. As a result of this, our planet is running a fever. If we look at global air temperatures, between 1980 and 2018, temperatures rose at an average rate of about 0.2 degrees Celsius per decade, leading to a 2018 global average temperature about 1 degree Celsius above the late 19th century. And this 1 degree of climate change we've experienced so far is already a pervasive risk multiplier. We're seeing it in an increased risk of wildfire, an increased risk of temperature-driven droughts, and increased flooding associated both with more humid atmosphere and higher sea levels. And it's this last that we're going to focus on for this talk. And sea level rise is of interest for many reasons, but one of them is that a lot of people live near the sea. About 380 million people currently live within about 6 meters of the high tide line, which are areas potentially vulnerable to permanent flooding from sea level rise over the next couple centuries. So we're going to take a deep dive on sea level rise to look at this topic. Since the early 1990s, scientists have measured changes in the height of the sea surface using satellite-borne radars, satellite altimetry. And if we look at the satellite altimetry record, what we see is that over this period, since 1992, there's been a relatively clear acceleration in the rate of rise of global average sea level. We've gone from about 2.5 millimeters per year in the early 1990s to a rate of about 4 millimeters per year today. And I think as all of you know, there are two main reasons for this. One is the transfer of mass from reservoirs and ice on land. I saw a bunch of glaciologists here earlier when I asked that question. And the other is expansion of the ocean as the ocean warms. There's a third smaller contributor from changes in the amount of liquid water stored on land with a direct human contribution there associated with the pumping of water to produce groundwater. If we look at the budget over the satellite period of the roughly 3 millimeters per year total we've seen, a little over half comes from the ice melting on land, of which the largest portion is due to mountain glaciers and ice caps, that's the GIC, but growing shares are due to Greenland and Antarctica. But the single largest individual factor is the thermal expansion of the ocean. Terrestrial water storage, there's a little bit of a variance in the estimates, but roughly it's a 10% plus or minus contribution to this overall change. But that's just global average sea level change, and nobody lives at the global average. If we're worried about risk or we're trying to interpret records, we need to take into account how sea level varies from the global mean. And you can see this just by looking at the satellite altimetry record, that these are very large and important processes. This figure from the National Climate Assessment is showing you the change in sea surface height as measured by satellite altimetry from 1993 to 2015. And you can see over this period, there's even areas that have seen a sea level fall, and there's some areas like the Western tropical Pacific that's seen a much more rapid than typical rise over this period. So why is that? Well, there's a few important factors. First, if we think about moving large masses around on land, whether that's land ice today or land ice in the past, those are really large masses of ice. And so moving those around have significant effects on things like the Earth's gravitational field and the Earth's rotation, as well as on the land itself. Just as a reference, to raise global average sea level by about 1 millimeter requires melting about 360 billion tons of ice. So you can see that's a pretty large number. Of course, 20,000 years ago, there was a large ice sheet covering North America, as far south as New York City. There was a large ice sheet in Northern Europe. And we're still feeling the effects today of those masses having moved around and deformed the mantle under them as they were sat and then retreated. So this map here is showing you one estimate of the ongoing effects of what's called glacial isostatic adjustment on sea level rise. And that's caused by the current flow of the mantle in response to the missing ice that's no longer there. So we see a sea level fall in blue in the areas that are under the cores of the former ice sheet, and a sea level rise along the edges of the ice sheets that is associated with the collapse of the bulge that was pushed up by the ice sheet when it was there. So this is an important factor if you're looking at sea level change, say, on the east coast of the US, where I do a lot of my work. But there's also effects associated with the contemporary changes in ice that fall under the label or rubric of gravitational, rotational, and deformational effects. So these maps here are showing you what's called a sea level fingerprint. So this is showing you the ratio of local sea level change to global average sea level change associated with melt loss from either Greenland on the left or the West Antarctic on the right. So in these figures, the areas in blue are areas that actually see a sea level fall in response to a shrinking ice sheet. And you can see that happens near an ice sheet. So for instance, if you melt Greenland, you actually get a sea level fall as far away as Scotland. And the reason for this is pretty simple when you think about it, even though it's counterintuitive. It's that ice had a large gravitational effect and was effectively pulling the ocean towards it. So if you lose that ice, the ocean relaxes away from it, even though you've increased the total amount of water in the ocean, so cause a global average sea level change. As you move farther away from the ice sheet, that effect diminishes, and a simple conservation of mass means that if you're seeing less than global average sea level rise near the ice sheet, you're seeing more than global average as you move further away. So if we're looking at the coast of North America, if Greenland melts, in New York City, we get about 50% of the global average sea level rise. In if the Western Arctic melts, in contrast, we get about 20% more than the global average. The story becomes even more complex when we move on to other processes. So not only do we have to think about, say, the expansion of the ocean as a whole when it warms, we also have to think about the fact that the ocean is not warming at the same rate everywhere. It's changing in salinity in some places, which also has affected on density. Ocean currents are changing, and winds are changing, and those too affect the height of the sea surface. So going back to a map similar to the one I showed you before, this is showing you sea surface height trends over 1993 to 2014. So the dark blues are areas of sea surface height fall. The reds are areas of high sea surface height rise. And all of these sorts of spatial patterns here, that's dominated by the dynamic sea level effect associated with the changes in currents and winds, and to some extent the distribution of heat. This is also, atmosphere-ocean circulation effects are also the dominant driver of year-to-year variability. So this map here is showing you the standard deviation of sea surface height over the satellite period. And you can see, for example, the large sea surface height signal that's associated with El Nino southern oscillation. So just want to remind you all at this point, I have an active channel open. So as we go along, if you have questions, please pop them in. So let's look at what's actually happened, starting with the instrumental period and then looking back a little further in time. So in the instrumental period, before the satellite record, our tool is our tide gauges. This is a photo of the Battery tide gauge site in New York City. I happen to have been married about 100 meters, 200 meters from it a few years ago, and has a great view of the Statue of Liberty. A tide gauge is basically in its simplest form, it's a stick that's fixed to the ground, and it has a floaty bit that floats and measures how high the floaty bit is above the fixed ground. So you can get from tide gauges records like these. This is average annual sea level at New York City, going back to the establishment of the Battery tide gauge in the 1850s. There was a little bit of a gap in the record here. And you can see since the 1850s, we've seen about 1.5 feet of sea level rise in New York City due to the combination of the factors contributing to global average sea level change, as well as a significant contribution from glacial isostatic adjustment. This map here is showing you the distribution of tide gauges around the world. So it's colored by start year. So the really dark orange ones, those are ones that date to the early 19th century. And then the lighter ones become more and more recent. And one of the things you see is that there's a very biased spatial sampling of tide gauges that reflects largely Western imperialism early in the period, and then the spread of them in a more decentralized fashion after decolonization in World War II. These were originally devices primarily for navigation and commerce, and so that's why we see the earliest ones in Northern Europe and in places like New York and San Francisco. So that poses a challenge as you try to piece together a global record from this. You have to use statistical methods that are comfortable dealing with a lot of missing data. And so we built a model in collaboration with my friends and Jerry Mitrovica at Harvard here, and our shared postdocs who've now gone on to their own careers, Carleen Hay and Eric Morrow, to try to address this question. We're not the first group to try to do this, but we've deployed a method that is very sensitive to some of these different spatial patterns associated with different physical processes. And I'm happy to answer more questions about our methods if you want to get into it in detail later. But broadly, we're using an approach that's based on something called a Kalman smoother that has this underlying model. So we're saying that relative sea level as measured at each tide gauge over time is the sum of some globally uniform term plus spatially varying terms associated with each of the different ice sheets and glacier regions, plus a dynamic sea level term, plus a contribution from glacial isostatic adjustment. And that the tide gauges are all measuring relative sea level, plus some additional noise term. Here, we're looking at some fits of that model, whose results are shown in gray, representing the 95% confidence interval, and black, the mean projection, for 5 selected tide gauges. So the reds are the actual annual tide gauge data. And you see that this approach smooths the curves, and it does, recognizing that smoothing, does a very good job of fitting the data in each of these places. It's one of the advantages of using what's sort of a non-parametric approach over some simple trend fitting. So we have a question: what spatial resolution of ice mass change is necessary for sea level rise estimates? I'll get to that maybe a little bit more when we talk about projections. But there has been, there is some difference between whether you're say losing ice from North Greenland or South Greenland. In this analysis, we haven't resolved that difference. So we're basically assuming that Greenland is contributing uniformly across it. The spatial length scale of those different fingerprints to think about is on the order of about 2,000 kilometers. So think of, going from Greenland to Scotland is how you go from, is how far you take to go from, a sea level fall to no sea level change. So it's a relatively long wavelengths associated with it. So small differences don't matter. But you can get some differences if you compare, say, a fingerprint associated with loss at the northern edge of Greenland versus the southern edge. This statistical model can reproduce the sea level field. So here we're showing our reconstructed field of sea level change from 1901 to 1990. So the dots are showing you the actual tide gauges, and the color is inferred using the statistical model. And one of the key things we get out of this is a reconstruction of global average sea level change. And this in red is our curve here. What we find is that from 1901 to 1990, global average sea level rose at a rate of about 1.2 millimeters per year. From 1993 to 2010, it rose at a rate of 2.5 times faster. So there's acceleration that started, at least before the satellite record, that is of a piece with the one that we see continuing in the satellite record. And in fact, there's an update to this analysis that Carlin Kay was involved in together with Sanke Dongendorf and others that came out this year, showing that the current acceleration really started basically in this period that you can see in this graph. It started in about the late 1960s and has sort of continued at a relatively steady rate since the late 1960s. So that gives us a 20th century record, and we can push it back a little more. But if we want to know how unusual this is, we need longer term context. So how do we get longer term context? We have to turn to the geological record. So here is a photo by a field team of some of my colleagues who actually go out and do the field work. And a lot of the best local relative sea level proxies come from salt marshes. So the idea has in the salt marsh you can see here is that you take a sediment core, you look within the sediment core at foraminifera that have particular tolerances of different salinities. And so use that to infer where essentially in the tidal zone, each layer of the sediment core was deposited. If you combine that reconstruction of where in the tidal zone each layer was deposited with a geochronological reconstruction driven by things like carbon-14, but because carbon-14 has a plateau over the last 200, 300 years before, also things like pollution horizons, nuclear bomb signals, and so forth. You get an age record, you match it up where the age record up with the location in the tidal zone, and you get a reconstruction of relative sea level at this height. So my collaborators, Ben Horton, Andy Kemp, and Roland Garrels, sort of pulled together from the literature and from an emerging set of new work, a global database of sea level reconstruction for the last 3,000 years. And this map is showing you what sort of the state of that database as it was a couple years ago. So these green dots are all salt marsh or mangrove records. So there's a lot in the North Atlantic, some in South Africa, some in Tasmania and New Zealand, along with a couple other types of indicators. So there are some interesting archaeological ones in the Mediterranean, things like Roman fish tanks that have very particular relationships to the tidal zone and give you pretty precise indicators for a very specific point in time. There's also things like other sort of biosedimentary features and coral microatolls that give you these sorts of records. So we take a simpler approach to the modeling because there's not as much resolution in the database. So here we're assuming that each sea level record is a combination of a global term plus a regionally varying linear term that reflects things like glacial isostatic adjustment, plus a non-linear sort of regional term that picks up things like dynamic sea level variability. And then we have proxies that are noisy measurements of relative sea level, but we also don't know the exact age of the proxies. So we have to take into account that we know the age with uncertainty. So we analyze this in a somewhat similar sort of Bayesian framework. Here we're comparing the actual proxy observations in red. So these boxes are giving you sort of vertical and geochronological uncertainties to the model results in black. And you see again, this sort of non-parametric Bayesian approach tends to give you curves that fit the data quite well. So here's the thing we're really searching for, which is our global sea level curve from this time period. So this in green is a geological record. It's also here's gray is the Hay et al. Tide gauge record, and purple the satellite altimetry record. And what we find is that 20th century global mean sea level rise, which from 1900 to 2000 was about 1.4 millimeters per year, is virtually certain to have been faster than during any century since at least 1000 BCE. So this 20th century rise really does stand out and is extraordinary. Now, I got one question: can the acceleration in sea level rise in the late 20th century be unambiguously attributed to ice sheet mass loss? The answer from Sanka Dongendorf's paper is no. The early part of that acceleration seems to have been associated more with ocean dynamic effects and ocean heat uptake. And it's sort of transitioned in this interesting way to being more dominated by the ice sheet contribution starting in the 1990s. So it may just be a coincidence that the acceleration itself has been fairly steady. What determines the uncertainty in the estimate? So this is a Bayesian analysis. It's a Bayesian uncertainty in the reconstruction of this relative sea level field here. So it's not explicitly the residual or scatter in the fit. We're doing essentially a Bayesian inversion and trying to say, okay, we have these proxy observations. Let's estimate relative sea level using Bayes' theorem, and it's the probability of relative sea level there. Oh, and I skipped over my cool thing. So yeah, we found that this was virtually certain faster than any century since at least 1000 BCE. So this is the only time that I know of president of the US has mentioned our work. Barack Obama tweeting when this paper came out, we're seeing the fastest rise in sea levels in nearly 3,000 years, punchline. So what does this imply for current and future change? There are a few things one might do to look at this. So first, I mean, I've just sort of told you one punchline, right? It tells us that something unusual is going on now, that this isn't just natural variability, but we can do a little bit more than this. So my collaborator, Klaus Bittermann, shown here, who was at the time a graduate student at the Potsdam Institute for Climate Impact Research with Stefan Rahmstorf, developed a statistical model, something that in the jargon is called a semi-empirical model, that relates sea level curve here to temperature. So the idea here is essentially that the change in sea level is related to a measure of the disequilibrium in temperature between sort of the sea level you already have and where sea level will eventually get at a given temperature level. So this is an approach that actually is similar to what was used for the first sea level rise projections by Vivian Gornitz in the early 1980s, but really sort of got revived by Stefan Rahmstorf in 2007. And this was the first semi-empirical model to be calibrated not just to the tide gauge data, but to a proxy-based reconstruction for the last 2,000 years. So we estimate this relationship between temperature and sea level, and we can ask a number of things. Probably the thing you would have the greatest confidence in using this for is to ask, well, what would have happened historically if something different had happened with temperature? So we can do that. We can take a few different ways of coming up with counterfactuals for historical simulations. So here, there's some of this in the Kopp 2016, but this is newer work. So the orange here is showing you what the semi-empirical model would tell you should have happened in the 20th century based on observed temperatures. And the purple is showing you what should have happened based on global climate model simulations of the 20th century. Then here we're looking at counterfactuals. So the purple here is a global climate model counterfactual where you take out anthropogenic greenhouse gases. The other two are sort of simpler counterfactuals where you assume either that the 20th century returned to the average over the last several hundred years rather than increasing, or actually returned to a declining trend that we see in the temperature records since over the last millennia. So there's some counterfactuals, and this is showing you the difference. So there's a lot here in the plot, but the basic takeaway is that depending on your assumptions about what your counterfactual looks like, it's very likely that between 8 and 18 centimeters of the observed 16 centimeters of global mean sea level rise over 1900 to 2012 is due to anthropogenic climate change. So somewhere between about half and more than 100%. Now, looking forward, what can we say about what might happen in the future? Well, one of the reasons I asked the question about RCPs, or representative concentration pathways, was to know how quickly to go through the next set of slides. Which makes the point that, when we ask about the future, we have to make projections conditional upon future human emissions. So this is showing you historic emissions of carbon dioxide. In 1960, we were at about 16 billion tons a year. In 2018, about 42 billion tons a year. And it's not really the role of the climate scientist. It's more the role of the energy modeler and other integrated assessment modelers to say what's going to happen in the future. But the climate science community, working with those communities, sort of developed a set of representative pathways that have been used for the previous generation now, the coupled model intercomparison project phase 5, to drive the climate model simulations. We're now sort of in a transition to a new set of scenarios that drove the coupled model intercomparison project phase 6. And I'm going to focus on 3 of these, shown here in red, yellow, and green. So the red pathway, representative concentration pathway 8.5, or RCP 8.5, is a pathway of continued fossil fuel intensive economic growth. Probably at this point, given sort of trends in things like renewable energy, a bit higher than business as usual in current policies. And this pathway sees a near doubling of CO2 emissions by 2050 and continued growth thereafter. The yellow one, representative concentration pathway 4.5, is one of moderate emissions reduction, sort of an emissions plateau through the middle of the century and then a decline thereafter. We're above RCP 4.5 right now, although maybe the derivative is somewhat close to it. But current policies put us, based on projection of current policies, a little bit above RCP 4.5. And then the green one, the one of rapid emissions reduction starting in 2020, leading to about a 70% reduction by 2050 and net negative emissions in the last 2 decades of the century, is the only one of these that's consistent with the policy goals set out in the Paris Agreement. So these pathways, RCP 8.5 leads to about 4 to 5 degrees C of warming over the course of relative to pre-industrial. RCP 4.5 about 2 to 3.3 degrees, and RCP 2.6 about 1.3 to 2.2 degrees. So as I said, RCP 2.6 is sort of the one that's most consistent with a nominal international target of keeping warming well below 2 degrees Celsius. RCP 4.5 is a little bit higher than, or a little bit lower than sort of current policies. So one thing we might do is take the statistical relationship we've identified and use it to project forward. So that's something that Klaus did in our paper. And what we find is that under a high emissions trajectory, if the relationship between temperature and sea level that we observed in the past 2,000 years continues to hold, we're probably looking at about half to 1.3 meters global mean sea level rise under RCP 8.5, about 0.2 to 0.6 meters under RCP 2.6. These are remarkably similar to the 2013 Intergovernmental Panel on Climate Change's projection. But they're also, that's, in some ways reassuring, but also somewhat worrying because the statistical model is assuming that a calibration based on a time when thermal expansions and mountain glaciers were the dominant drivers of global mean sea level change will continue to hold in a period when we're seeing accelerating contributions from ice sheets. So if we want to project global changes, we might want to take a different approach that doesn't necessarily assume that statistical approaches continue to hold. It's also projecting global mean sea level directly is a little bit limiting because we care about regional sea level changes, and you need that broken up into different processes in order to take the global mean sea level change and relate it to local sea level change. So do those estimates I just presented include contributions from the ice sheets? Well, the IPCC numbers do. The statistical model, you can't say. It's not resolving the individual processes. It's just saying, here's the statistical relationship we see over the last 2,000 years between global mean sea level and temperature. How can you be confident in these projections given that the 20th century record had variabilities and plateaus that are different than CO2 and temperature? Well, something that they're not actually that different than CO2 and temperature. You can't see it there. There were plateaus in the temperature record as well, and so there's an effect related to aerosol forcing sort of in the immediate post-World War II period. But I'm not telling you necessarily you should be confident in this set of projections. I'm telling you that the statistical relationship over the last 2,000 years would give you this. So I want to take a different approach, actually, because I want to probe whether this is a good approach. And so we've also taken an approach, which is a somewhat more commonly used approach. It's what underlies, it's a variant of what underlies the IPCC's fifth assessment report, but where we're looking at each of the processes individually. So this is a sort of bottom-up accounting-based approach, where we're drawing upon different lines of information for each process and then assembling them. So here is our figure showing you our different processes that matter for regional and global sea level changes. So in this set of projections for vertical land motion, we're drawing on extrapolation of historical trends. For land water storage, we're looking at the relationship between historical demand for dam construction, historical demand for groundwater and population. So we're going to use population projections to project that going forward. For thermal expansion and ocean dynamics, these are sort of the areas where global climate models sort of do their best. So we're using global climate model projections here. And then for ice melting, ice contributions from ice sheets, we have to use mixed methods. For the glaciers, there are glacier models driven by climate models, and theirs goes in. For the Antarctic and Greenland contributions, even still today, but especially a few years ago, that the ice sheet models are at a relatively early stage of development. So in our primary projections, which I am about to show you, we sort of used an approach similar to that of the fifth assessment report of the IPCC, which was based on a sort of expert assessment of the literature, but we also brought in information from a process called structured expert judgment to figure out, not just what is the most likely thing based on the literature, but how does sort of high impact, low probability outcomes relate to what is most likely. I'll talk a little bit more about structured expert judgment in a couple minutes because we did an updated structured expert judgment study that I'll talk about. I have to say our framework, the framework for projecting probability distribution of future sea level change based on this bottom-up assessment has become widely used in the US and underlies official projections in Washington, Oregon, California, Maryland, Delaware, Boston. It has an important role to play in the national climate assessment scenarios. And we did a set for New Jersey that is being transformed and updated for a set that will be official projections for the state. So just to highlight sort of these numbers based on accounting, they turn out to be quite similar for our IPCC consistent approach with the semi-empirical models. So for 2030, we're looking relative to year 2000 at about 10 to 20 centimeters of sea level rise, almost regardless of emissions pathway. For 2050, about 20 to 40 centimeters, and emissions pathway has very little effect through 2050 because of the lags in the ice sheets in the oceans relative to changes in forcing. And then by 2100 in these projections, and 50 to 120 centimeters or so under RCP 8.5, around 30 to 80 centimeters under RCP 2.6. But as those of you who are in the room who are glaciologists will be intimately aware, the physics of the interactions between ice sheets and the oceans is complex, and the state of scientific understanding is rapidly evolving. For instance, there is very active controversy in the ice sheet world about the role of marine ice cliff instability, which has to do with the gravitational instability of cliffs of ice, such as this one pictured here from a photo New Christensen took in Greenland, under their own weight. Some work by Rob DeCanto and David Pollard suggests that marine ice cliff instability could lead to relatively rapid increases on the timescale of about a century in the Antarctic contribution in areas where the Antarctic is sitting below sea level, and the Antarctic ice sheet sitting below sea level. But this is, I would say, still highly controversial. But if we're thinking about risk assessment, we don't want to just ignore something because it's highly controversial. We won't want to say, well, this highly controversial thing is definitely correct. What we want to do is say, okay, well, what is it with it? What would happen if it is correct? What are the implications? So we did that in collaboration with Rob DeCanto and David Pollard. And what we find is that out to about 2050, it doesn't much matter whether or not you include this process. Out to 2100 in a low emission scenario, it also doesn't much matter. You don't trigger these sorts of instabilities in a low emission scenario. But potentially, if some of this modeling is correct, you might in a high emission scenario. So instead of the 50 to 120 centimeters we projected, if Rob and Dave's 2016 analysis were correct, you might get as much as 90 to 240 centimeters of sea level rise by the end of the century due to the gravitational instability of ice cliffs and the loss of ice shelves in particularly the West Antarctic, but also in some places in the East Antarctic. Now, that's one study. And so what we wanted to do is say, okay, well, how does the current state of the literature as a whole translate into expert assessment? So we used an approach that was developed in the social science literature called structured expert judgment, which is a way of using calibrated expert input to estimate probability distributions to get a sense in early 2018 of sort of where the field was thinking, not just about what was most likely, but also about sort of these lower probabilities, high impact possible futures. So what you do in structured expert judgment is not simply an expert survey because it's calibrated. You're getting people, a group of experts, about 20 together, and then you start by asking them questions to which the answer is knowable. Things about, say, past changes in ice sheets or sea level. And then you're using the questions, those questions, not just to estimate, are the experts accurate, but are they accurate at estimating their own uncertainty? What you're looking for is to give the most weights to experts who give reasonably accurate answers, but particularly are not overconfident. And so this approach has been used for about 30 years to look at things as broad ranging as food safety and nuclear reactor safety. There was an earlier ice sheet study in 2013 that we updated and published in Proceedings of the National Academies of Sciences earlier this year. So I'm going to add a set of bars to this plot that now reflect this new assessment of the ice sheet contribution. And what we see is not a huge change again in 2050. In 2100 under low emissions, slightly fatter tails than either of these two studies. The experts are reflecting the fact that there are things they're not confident about that might give you these fat tails. But if we look at the high emission scenario, the median is pulled down relative to the DeConto and Pollard paper, but there is a fat tail reflecting the fact that the community is not confident in excluding some of these high-end outcomes. So the low end is pretty similar to the work we did originally, consistent with the 2013 assessment report. The high end is consistent with some of these most aggressive models. So, punchline from the expert assessment would be about 40 to 130 centimeters under low emissions in 2100, about 60 to 240 centimeters, most likely towards the low end of that range under high emissions. So this poses some problems for risk management. Let's think about a 100-year event, a high water event. So in our baseline world, year 2000, without sea level rise, we would expect a 1 in 100-year event to happen every 1% chance in any given year. So this is a 0.01 number of expected events per year everywhere in the world. But if we look through to 2050 under our more conservative assumptions, we see that starts to change pretty quickly. In some places, even under these relatively modest projections, we're seeing the 1 in 100-year event more than once a year. In New York City, we're seeing it with about a 1 in 25 probability in each year. In 2080, this continues to increase. Many more places are seeing the 1% probability event more than once a year. In New York City, it's about 1 in 2 years. And that's under low emissions. Under high emissions, it's about once a year, again, under the more conservative sets of projections. If we bring in the more aggressive sets of projections, we could be looking at the 1 in 100-year event 20 times per year in New York City by 2080 under high emissions. So what do you do if you're making infrastructure, land use, or buyout decisions that will affect vulnerability in 2080? Yet different reasonable approaches indicate that we should expect a 100-year extreme sea level event on average, maybe once every other year if we keep emissions down, once a year if we don't, but we're relatively lucky in how the ice sheet responds, or 20 times a year if we don't, and it turns out we expect the unexpected from the ice sheets. Well, the first thing we need to think about is that the consequences of our decisions today often last longer than we might initially think. This photo here is a photo of the Marion Power Station in Jersey City, New Jersey from 1911. It was established by the Public Service Electric Company, which was Thomas Alva Edison's company. It was replaced by the Hudson Generating Station in the 1960s, which closed in 2017. This is a map from the Electric Railway Journal of 1917 of the New Jersey and New York City electric grid. That's Marion, there in the red star, which flooded in 2011 during Irene and in 2012 during Hurricane Sandy. These are 14 major switching stations in the PSE&G grid in New Jersey and that were flooded during Sandy, contributing to the loss of power throughout the state for, in some cases, as much as 2 weeks. Of these, 7 of these are at 7 of the 14 are at locations you can see on this 1911 map. So the decisions made before 1911 about how to structure the electric grid affected the vulnerability of New Jersey to Hurricane Sandy in 2012. Right? So these decisions can have quite long-term consequences. So what do? We have a number of approaches, right? We could just ignore the problem. We rebuild essentially unchanged. Maybe even after a disaster, you become a little bit more gentrified, and assume that the system of subsidies that allows that to happen in terms of flood insurance and disaster relief will continue indefinitely. Maybe that will, but I would be very nervous about that assumption. We could turn to accommodation. That is, how do we make our communities more resilient to occasional flooding? And sort of the visual example of that is something like elevating a house, but it also includes things like improving emergency response. But one of the things you have to bear in mind is that elevating houses or individual buildings on sort of the individual basis is of limited value if you don't also do this at a community scale. You know, he might be safe in his nice house here in the aftermath of a hurricane, except that he might have flooded sewage and no electricity because the critical infrastructure wasn't also protected. We can build hard infrastructure. So this is a diagram of the proposed Eastside Coastal Resiliency project in Manhattan. And here the idea is to build out the land, put in some berms and other structure and levees, has parkland to keep water out. But as the people of New Orleans know very well, you need to plan for those occasions when hard protection fails. You know, everything has a risk of failure. We can expand protective natural infrastructure. Here are some new oyster beds in Jamaica Bay and a salt marsh, and things like oyster beds and salt marsh are quite good at dampening wave energies, although they're less good at dealing with longer term elevated sea levels. Or do we relocate? And here one photo from a community, Oakwood Beach in Staten Island, that decided to do just that after Hurricane Sandy, giving up their community to parkland. A key question is, how do we decide? I don't think this is a problem for which there is one single answer that can be opposed from above. It has to be determined through a deliberative process. And this is an area where large public and land-grant universities, I think, have a very critical role. An area where we in New Jersey have been doing significant work to help facilitate community processes. Here's an example from Woodbridge, New Jersey, where our agricultural experiment station has helped facilitate the design of a resilience plan for some areas in that community that have been badly flooded several times. But as we think through this, we have to recognize that deep uncertainty I was talking about. We don't know whether we're looking at a flood, you know, a 1 in 100-year event every 2 years in 2080 or 20 times a year in 2080. And we probably, if we can avoid it, don't want to plan as though we are certain that it's going to be 20 times a year. We instead want to take a flexible approach where possible. Be cognizant of our contingency plans. What will we do when we get to 1 meter of sea level rise? What will we do if we get to 2 meters of sea level rise? What options are available to us? And not just postpone those decisions, but actually plot those out in advance. This is an approach that's known as flexible adaptation pathways, and I think it's key when we're dealing with this sort of deep uncertainty. But to do that, you need to train people who can help facilitate the interactions among scientists and engineers and communities on the ground and other stakeholders. And that's something we started doing a few years ago at Rutgers with support from the National Science Foundation through our Coastal Climate Risk and Resilience Initiative, which trains graduate students in natural sciences, engineering, urban planning, landscape architecture, to work together, social sciences, to work together, to work with communities so that they can, you know, both be researchers who do use-inspired research that can actually help solve problems while still yielding fundamental insights, or go on to careers where they're sort of at this boundary worker position, helping translate between scientists in the academy and communities on the ground. Some words of caution for physical scientists if you're trying to get into this space. Well, so one thing is that sea level change is just one boundary condition on a complex cuspal system. Coastal evolution requires accounting for interactions of sea level change, geomorphology, socioeconomics, and human responses. So we have to go into this with some degree of modesty. It's not a sea level process. And even the best designed processes can fail or lead to unintended outcomes if they aren't sufficiently aware of political economy. Processes can be hijacked, for instance, by developers and go in a direction that may not actually increase resilience. So these are things that we have to approach with modesty as physical scientists. However we choose to adapt, the starting point is climate change mitigation. There's a large difference between these high emissions projections and low emissions projections. And with that, I want to conclude. Sorry we got started a little late, and so I ran a little long. But if people want to stay and ask a few more questions, I'm happy to do that, or we can move the discussion into the session in a couple hours. So thank you.
Thank you, Bob. I think there could be some science questions if someone wants to stay 5 minutes. The hard science questions, and then there's great material to continue the discussion during the Q&A at 12:30. It's only 30 minutes from now. No, an hour from now. 12:30 to 2 at the second floor conference room. Any questions?
So I see one question asking is there any pattern to the residuals in your sea level fit? So that depends on which fit you're talking about, right? We're talking about paleo or future. In the paleo, not especially. In the future, I think there are some assumptions that we made in doing the analysis that I think if we wanted to go back now and do it again, we would tweak. But for instance, you know, the residual term in this analysis is being forced to pick up things like tectonic effects in Japan. So it's picking up some things that do have some spatial structure because the way this was set up, you know, GIA was the only land motion term in it.
I have a question, Bob.
Yeah.
You showed scary projections for 2100 when you do all of these more complex physical processes on ice sheets. Is there any past climate change or some past climate interval where you could test those processes and be confident whether they work one way or the other?
Yeah. So yes, there are things one might hope could do that. The last interglacial, you know, about 125,000 years ago, has been used as sort of a key test point for ice sheet models because it's sort of the only period over which we can get even somewhat precise sea level reconstructions during a somewhat warmer period. So global average surface temperature during the last interglacial was maybe about 1 degree above pre-industrial. So during this period, sea level, based on work that we did about a decade ago and on some work by people like Andrea Dunnan more recently, looks to have been about 6 to 9 meters higher than today. So it's complicated to interpret that. It was a little bit warmer. Earth's orbit was also different. It was more eccentric. It turns out from work that my postdoc Daniel Guilford is doing with ice sheet models that if we could constrain the Antarctic contribution to that to be either relatively high or relatively low, it could be quite informative on the role of processes like marine ice sheet instability. But unfortunately, if the Antarctic contribution turns out to be sort of in the middle of current estimates, it's actually not very informative. It allows a broad range. So we actually have a paper that's about to be submitted looking at, you know, the potential of the last interglacial to constrain ice sheet models. But I think the punchline at the moment is it's a significant potential if the answer of the Antarctic contribution to the last interglacial turns out to be towards the edges of where we think it is, but not that useful if it's in the middle. Are there realistic assessments of coastal impacts under all RCPs that account for municipal zoning restrictions globally? No. The best we can do right now, well, so there are assessments, and actually we're working on one with as part of the Climate Impact Lab that looks at sort of where property is right now. So I guess to the extent that you're saying, okay, it looks at the distribution of property reflects those zoning restrictions, current zoning restrictions. We're getting there. There have been some simplified approaches that allow basically on each coastal segment an agent to decide going forward, well, do we stay there or do we retreat or do we build a wall? That's a very idealized representation. But those idealized sort of neoclassical economic models suggest that if you do respond adaptively to changes in sea level, in an optimal fashion, you could probably reduce damages about 90%. There's also some work that we did as part of a book that was published a few years ago, suggesting that if we were making optimal adaptation decisions in the US right now, we would cut damages from coastal flooding about 85% in the US. So, these optimal adaptation models have to take into account a variety of factors that, including political economy, that cause non-optimal adaptation. I'm not sure exactly was getting at your question, but hopefully that's somewhat helpful there.
Awesome. I think we should wrap it up here. If there's no other questions, and we'll see you in an hour.
Excellent. So I'll do one last question about the fingerprints. So those come from sea level theory, which is also has to be used by the GRACE people to interpret it, because GRACE gets a aggregate gravitational change. So you have to use the sea level equation, which is the sort of gravitational balance plus rotational effects, to calculate fingerprints. Our fingerprints that we used in our model assume uniform loss over individual glacier regions, and they had uniform loss from West Antarctica, East Antarctica, or Greenland, and those are areas where we're refining, and in the next iteration, switching to things that look more like the best fit patterns based on GRACE mass loss patterns. So the fingerprints are reliable near the coasts, except near the coasts, I would say, of the ice sheets themselves, right? Because what's weird, it's really close to the ice sheet where the differences in where the differences in how mass is distributed make the largest difference. And if you want to come back to that during our question period, I can show you some figures from a paper that we published a couple of years ago.
Awesome.
All right, thank you all very much. As I said, this was an experiment for me as well as for you. I hope it went relatively well, and I look forward to talking in a couple hours.
See you in a bit.
Great. Thank you.
Thank you. There's still room in the Q&A if you want to come. Lunch for 5 more people.